Hello, welcome back to the next lecture in this series of operating systems kind of stuff, low-level computing. I'm going to carry on from where I left off in the last lecture. So if you remember, in the last lecture I talked about how the computer boots, and we looked at how we could, by using a hex editor, we could write bytes directly into a file and then use that as a sector on a hard disk or a DVD to boot the computer and to run that low-level code. Just to clarify one thing that I don't think I mentioned last time, you mustn't mistake reading sectors from a disk with reading files from a disk. So at the lowest level, the way the disk gets accessed by the machine is by it just indexes sectors. So it says, I want sector 0, I want sector 1, 2, 3, 4, and it pulls a whole chunk of bytes off. So that's at a low level. And then at a high level in the operating system, people develop file systems, and a file system is just really a simplified way of looking at it. It's just another indexing system for the data on the disk. So when I want to load a file from the disk in, say, my Windows or my Linux operating system, I open the file, and what that means is the name of the file and the directory that it's in will map onto a sequence of sectors on the disk that have the file's contents in, and the file system that I'm using, whether that's NTFS in Windows or ext in Linux, whatever it is, it'll have some mapping to the sectors and it'll read those off. But this happens at a very high level, really, and we're working below that at the machine level. So when I talk about writing a boot sector to the disk, I mean we actually write a chunk of bytes directly to the disk. Okay, there's no file system involved. It's just we just view the disk at a low level as a sequence of sectors, and the boot sector is the first sector. Okay, so in that last lecture I was editing the boot sector in hex, but I showed that we could create something. We could create an endless loop by putting the machine opcodes in there, and those bytes that we typed in meant something specific to the architecture that we're using, which is x86, which is it's probably the most widely used computer architecture. So we typed those things in, we padded out the boot sector to 512 bytes long, and we put the magic number at the end so that the BIOS in the computer, when it starts up, it knows that this is code that it can run rather than just data on a disk. So it knows it's a boot sector. So it was quite tedious to write that in a hex editor. The problem is, well, it's tedious to do that, but also, if we want to write a program, we've got to learn all of the machine code opcodes for the things we want to do. If we want to, move data around between registers, I'll talk about registers today, and all of those things, then we need to learn what all the opcodes are. So this is why we often use an assembler. And the assembler, you type in, it's not really high level because you're still writing very low level machine codes, but you can use names like, you can name the registers, you can name the instructions like jump. To compare values, you can use the comp function, and the assembler literally just translates those into machine code. So it's quite a simple process, really. It's just a case of the assembler looking up a table of what those assembly instructions are and mapping them to machine codes, and then it creates the boot block just like we did in our hex editor. So I'm going to try and show that to you with some examples now. Yeah, so that's what we're going to do. Today we're going to look at assembling some code for our boot sector, and then we're going to learn about registers and interrupts, and using those we're going to demonstrate how we can tell BIOS to print a character to the screen, and that's quite a good thing, because then we're learning more about the computer. Interrupts and registers and BIOS are fundamental to understanding the boot process and how a computer starts. Once we understand these things, we can build up and learn more about assembly and more about the computer. But we'll just start like this. Okay, so by the end of this, what we should have is a little assembly boot sector program that just says hello world, and we can run that. We can boot a computer with that, and our code is running at the lowest level then. So it's a nice result. Okay, so well, where do we start? Let's look at assembly then. So what I'm going to do now is, in the last lecture when I wrote raw hex code in my hex editor, I'm now going to do the same thing but using an assembler to write the code, and that will transfer into my boot sector, and we can look at that in a hex edit to see how it, how it relates to what we did before. So, well, first of all, I'm going to edit a file. Called my boot sector. So if I go we'll call it boot sector. Boot sector.asm. So this is going to be my assembly source file. Okay. Now, well, this is my assembly code now. So what I'm going to do is I'm going to play around with the assembly instructions, and then I'm going to compile those with my assembler. I'm using a thing called NASM, which is quite a popular assembler. There's not really much difference between assemblers. They just take the sort of more human-friendly view of the machine code instructions and translate them into opcodes. And there are slight variances between them, but they pretty much do the same thing. NASM is quite a nice one to use, I find. So it's open source as well. All this stuff is free. So what we're going to do, well, let's just start off with an instruction. So I'm going to do this thing here. If I put this loop, okay, now this bit of assembly, all it means is I've declared a label here, which is just really a human-friendly mapping to an offset within my assembly code. I'm going to show you the hex so this will become clearer, but then I've got this jump and it's saying jump loop. So what this will translate to when I compile it is, because this label is right at the top of my file, at the first instruction it's going to be 0, so this is going to say jump 0. It's going to jump to itself. We're going to get an endless loop. So if I just compile that, or assemble it, if I want to use the right terms, I'm going to use this command here. So this is NASM, and what it's doing, it's taking the assembly file that I just wrote here, this one, and it's going to output the machine code in this file. I've just called it .bin and I've called my source.asm. It doesn't really matter what the extension is. We just need to know that this is my assembly code and this is my binary code that will become my boot sector. So these are just raw bytes that are going to go straight to the disk on the machine, and they're going to be loaded by BIOS and interpreted as code when it starts running. So I've got this option here, fbin. Now really this just means that when it's just telling the assembler that I just want a raw machine code file, I don't want any metadata in there or anything like that. If we were compiling a program in assembly to run on an operating system, then often you have lots of extra metadata in there to tell the operating system how to load the file, and you have different sections, some for data, some for text, things like that. So by putting fbin in there, I'm just saying take my assembly, compile it just to raw bytes, no metadata in there, just the raw, just translate it directly to the raw program. Okay, so I'm going to run that. It's very quick, it's very fast because it doesn't really do much, it just translates the names into code. So now I've got my boot sector. So the first thing I'll do is just open it up in a hex editor. So I'm going to look at ghex again. Like I did in the last lecture. So I'm editing my file. Okay, what do I see? Well, all I can see in here is there's 2 bytes. And it's these numbers here. So EB and FE. So these are hexadecimal numbers. Well, why is that then? These are just, the assembler has just translated my jump instruction into these 2 byte codes. So that's all it's done, it just mapped them into the machine code instructions. Now if I tried to load this as a boot sector on the on a computer now, it's not going to run, because it's, first of all, it's not 512 bytes long, and it's not got a magic number at the end, so I need to figure out how to do that in my assembly code. So I'm going to show you how to do that now. But that's it, that's a jump instruction in hex. So remember, the computer, it just understands numbers. It doesn't even, when I type jump, it doesn't know what jump is, it just knows what an opcode for the jump is. And this is all processor specific, and I'll reference more of this stuff later on, but you can get the like the Intel x86 developer manual, and you can look at all the opcodes and look at all of the different features available for the processor. But we can do that later. So, okay, so we've compiled some code. Let's play around with some other things then. So I've just put a jump instruction in there. It's quite a nice one to start with. We can put comments like this. So if I put a comment, or we can put them here, another comment. So these just get ignored when it compiles it. Now, I mentioned before in the last lecture that the computer doesn't really differentiate between code and data. If you start the processor executing at a certain address in memory, it's going to assume that it's code. It's going to try and execute it, and if you jump the code, then it will run the code. If you jump into data, then it will interpret that data, so those bytes, as opcodes, and then try and run them. Often when you end up accidentally jumping into some data, it often happens when you get memory errors in C, and you end up jumping into some data, and you can start executing that data, and usually it will crash because it's meaningless. There's no real logic or sense to the opcodes that it's interpreting. So there's no difference between code and data at the low level. But often in programs we need to declare data, we need to declare strings, default values, stuff like that. So the same with this assembly, we can declare data in it. We've just got to make sure at this low level that we don't allow the computer to start executing that data. But as I work through this, we'll see what that means. But if I put db 0 here, what this means is it means a data byte. It just means it's not an instruction like jump or move or something like that. It's just saying stick a 0 directly into the output, the binary output. So let's see what happens when I run that. So I compiled it again, and now I'm just going to edit it. There we go, so we just got a 0 on the end, so an extra byte added. So now we've got 3 bytes in our boot sector. Let's put another one on there. So if I do db, I don't know, let's put 1. And we run it. It's often nice to play around with things like this to really understand how the assembly is working, so that you don't just assume things are just magic. You can just play around with little examples, see what code it generates, and and then you can really understand how it's working. Sometimes when you see tutorials and things, they just talk about, here's some opcode and stuff, here's some assembly, but they don't really encourage you to look at, to just try, compiling simple things and looking at what the output's like. It's often very useful to do that in C, and we'll do that later on. We'll take C code, we'll compile it and look at what that looks like in assembly, to understand how C works. It's a really nice way of learning, so that you don't miss anything out. So now I added that db1, and I've got 4 bytes now, so I've got the 0 if I look at my code. Yeah, so this jump statement, jump loop, this translates to these 2 bytes here, which are opcodes for the jump statement to jump to itself. And we've got db0, which creates a byte here, and db1, which creates a byte here called 1. Okay, that's good. So let's just declare some more data. Now if I do dw, and I do 1, 2, 3, 4, this is declaring a word, and a word is well, in this case it's I've got db0, db1, and I've got, so these are bytes, these are single bytes, and a word is just 2 bytes, okay, so it's just 16 bits. So when I compile this, I should see 2 more bytes added to the end. So I compile it and I edit it. There we go. So now I've got 2 more bytes. Because I declared a word which is 2 bytes, it's a 16-bit value. But you'll notice the first thing that's important, I bring this up, I declared this value, this 16-bit value, 1, 2, 3, 4, and if we look in here we'll see that it's actually the way it's written to the file is in reverse order, so it's 3, 4, so it's the least significant byte first, and then it's 1, 2, the most significant byte last. So this is because x86 processors, they are little endian, which just means, and I always get them mixed up when I think about it, it doesn't really matter, just to understand what that means and to understand which, on whichever process you're working, how that translates to how things are stored in memory. But yeah, so this means if I declare a multi-byte type value, so here I've got 16 bits, 2 bytes, it will always get represented in memory in reverse order. So, and on disk as well. So there we go. Now, if we want to make sure that our boot sector is 512 bytes long, and then put the magic number at the end. So first of all, let's do the magic number. So, if you remember from the last lecture, the magic number was, well, we put in our code, we put this, didn't we? If I just compile this and look at it. So there we've got AA55. Actually, it should have been the other way around, it should have been 55AA, and I sort of did that on purpose really, because it's little endian and we've got to get them the right way around. The actual 16-bit magic value is this, AA55. And that's right, so this is starting to look like our other boot sector, so we had this magic number at the end. And this magic number is important so that the BIOS, when it loads the sector, it decides that it's code that it can execute, otherwise it will skip past it and look for another drive to boot from. So that's good, but now we've got to pad it out so that this magic number comes at the end of the 512 byte block. So we can do that by padding it with these data statements like this. So I could put a whole lot of these in. I can compile it and edit it. There we go, I've got some more in. So I've got to make sure I've got enough in to make it 512 bytes long. So, well, let's think there. We've got 2 bytes there. We've got 2 bytes there. We've got to make sure it's 512 long. So if we add 512, 508, I think, then it should make it the right length. So 508, did I say? I'm purposely doing it like this so we start to understand how the assembly works. So if some of you have done this before, you might find it a bit slow. If you've not, then hopefully you'll find it useful. And we will get into some quite heavy stuff later on, so it's good to take our time now. So I want to make sure there's 512 bytes in the sector, so I think I said if I have 508 of these, then it should make it the right size. Now there's a little shortcut here where I can say times 508, and that just means duplicate this db0 508 times when it comes to compiling this. So let's see what happens. There we go, we've got lots more zeros now, and that looks, is that right? That's not quite right, is it? It's just, so we should be, oh no, So this is why I'm going to show you how to let the assembler calculate this for us. But yeah, we see that if we can put loads of those zeros in, we can pad it out and we'll get a boot sector of the right size. If I just close this, one way I can check the length of it as well is if I just do, I can use LS. So it's 512, so that's right, so it should boot now. So let's see what happens. So I've got my jump, my endless loop, and I've padded it out. I've got the magic number on the end, so we should be able to run this. I'm going to use it in QEMU, which is a computer simulator, an x86 simulator. I could write it to an ISO file like I did last time and run it in a virtual machine. But it's often easier to work with emulators when you're doing this stuff. So let's just run this. So it says it's booting and it's gone into that endless loop. Let me just show you what happens if I get my code slightly wrong. So if I put 500 and I don't know, if it wasn't quite long enough. I compile it and let's try to run it. There we go, look. So because I've not padded it out and the magic number's not in the right place right at the end of the first sector, then the machine doesn't know, it doesn't see it as being bootable, so it just carries on looking for other things. It's trying to look for a network boot drive because there's no hard disk, there's no CD in there that can be bootable. So this is good. Okay, so we're writing our boot sector in assembly now, which is much easier than working with hex. So another thing we can do here, which is often useful, if that was 508, if I add some more stuff in here, like, I don't know, let's put another jump statement in there, jump. This can also jump back to loop, it doesn't really matter, it's never going to get reached. But if I run this now, compile this, and then I run it, oh, it's not bootable again. And why is that? It's because I'm adding too many zeros now because my machine code instructions it's got this extra jump in, so it's made it longer. Let me just look at the hex for that code. So here we see we've got our two jumps here that are both the same, but look, we've gone over the boot sector size, 512 bytes, so the magic number is no longer aligned at the end, it goes past it. So one thing that you often see when you see some assembly code is the use of these little, well, they're sort of like placeholders, but if I, just to explain this, what I'm going to do is put some of these things into my code. So if I say db and then put this $, I'll put a few of these in just to show you how this works. Okay, what this means when I put a $, is it means just when it's writing the machine code, just put the location, the offset of the current instruction into the machine code. So the offset of this one is one more than the offset of this one, so you can see this will increase. The easiest way is to compile this to see what it does. Okay, so we see there 2, 3, 4, 5. So this is actually the offset in the binary file of that instruction. So that will be 0, that will be 1, this will be 2, 3, 4. So why is this useful? Well, something else we also are going to use is another one of these special assembly symbols, is this one. So double $. If I compile that and then look at the hex again, oh, well, it's a bit difficult to see this because these are all zeros, but actually that was 0. If I put more of these in, I'll just put this one at the end so you can see, differentiate between the zeros. So I'm going to put a 1, 2 in there. This will become clearer soon. So okay, that double dollar sign, it's just put zeros in here, and basically what the dollar signs do is the single dollar sign is the current offset in the file, the current byte. So this would be the address of this instruction, the offset from the start of the binary data, and this would be the next one, this would be the next one. But double dollar sign just refers to the origin. In this case it's just 0, but we'll see that we can change that later on. Anyway, what this means is that if we write something like this, if we want to make sure that our boot sector is always padded to 512 bytes, then we can say 510, because the last 2 bytes of the 512 bytes are occupied by the magic number, this 16-bit number here. So we want to pad it with zeros all the way up to there with 510 to make sure that this 510 bytes before this last byte. So we can do this using those funny dollar signs that we saw. So this is just saying, because this is 0, it's just saying take 510 minus the offset of this instruction here, and that's the number of times we want to write zeros into a file. So let's just do that. There we go. So it's padded to 512 bytes. And if I had some more stuff in here, db 1, 2, db, I don't know, whatever, it doesn't matter. Another one we can do is we can fill it with a string as well. This just, all this means is it just writes the ASCII values of this directly into the output. But what I've done there, so I've added some more stuff, so it means that hopefully it should still be 512 bytes long, because this accounts for the relative offset of this instruction when it pads it out. You never really have to worry about this stuff. I'm just trying to explain it so you know how it works and what those things mean when you see them in code, because often you see something weird like that and you think, why does that look like that? So let's have a look what we've got now. So I've put those extra things in there, and let's just check. Oh, it's still 512 bytes long, so that using those dollar signs to work out the number of zeros to add was good. Just to show you as well, we've put a string in there, and you can see that here, you can see the ASCII characters in the hex editor for that hello string. So it literally just wrote those values of the string in there. There's something we can check while we're doing this. Like I said, it's good to play with things, and I can't remember exactly if this does what I'm going to check for. I'm going to stick on the end of here 66, and what I want to know is how many bytes this stores. In C, when you have a string, it often ends with a 0, a null terminator, so I'm going to see my assembly whether it puts a 0 on the end of that string or not, and we'll see that it doesn't, so it doesn't write a 0 on the end, so you have to do that manually. You don't need to worry about that just yet, but it will be important later on. So what we've seen so far, now we know how to create a boot sector in assembly, and now we just need to learn a bit more about some assembly instructions so we can make it do something. And I said before that we're going to be printing a hello message to the screen soon. And remember, there's no operating system. We're behaving like the operating system. There's nothing else we can use other than BIOS at this stage to do anything. So I'm going to show you how we can help BIOS, how we can use BIOS to help us output some information to the screen. So, well, let's leave a bit of this code in there because it will be useful later on. So I'm going to talk about registers now, and then I'm going to talk about interrupts. We need these things but when I put them all together we can see it running. But in a processor you've got the processor can access memory, and it can read and write to memory, and you can stick loads of memory in computers these days, gigabytes of it, and that's very good for storing stuff. And when you're processing data, having so much memory is very good. But a processor, relatively to the speed of the processor, accessing that main memory is very slow. But processors have a very small amount of very fast memory very close to them, and probably one of the fastest pieces of memory you can access is the registers, and there are a few of these, but the processor can use the registers to store information in, to store bytes and words. Whilst it's working on stuff, it can store something in a register, add something to it, and then store it in another register. And you can think of them as variables for the CPU that you can use for doing things very quickly on. And some instructions can only operate on a register. So if you wanted to do something like add two numbers together, then you might have to store the first number into the register and then add the second number to the register value. And in these cases it's just because that's how the architecture of the CPU works. And often it's because the simplicity of the hardware of the processor allows it to be very efficient and very fast. So that's why we've often got to do things like that. That's why we can't write high level code in assembly. Anyway, let's get on with it. So just to explain registers, I'm just going to write some assembly here, and we'll just check that it compiles so I know that I've written the right instructions. The other thing with assembly is it's very difficult to remember it, if you're not using it very often, which I don't, and most people don't. It's very easy to forget the opcodes and stuff like that. But the point is, if you understand it, then you can always come back to it. You can look up what opcodes you need. If you can understand the theory and how it works, the essence of it, then you can pick it up. So excuse me if I typed the wrong thing, but this is how it goes. So first of all, we have, I'll just write them as comments, but we have a few general purpose registers. Now there are quite a few registers, and I'm only going to talk about a few of them and how they work. Later on we'll look at how the other registers work. Some registers are general purpose, which means they have no other use than just for storing information in, whilst you're working on bytes calculations. But other ones have special meanings. They might also be general purpose registers, but they might have some other meaning. They might be modified in some way when you call a certain instruction. For example, some instructions decrement values in certain registers. So you do have to understand these relationships between registers and the CPU. And if when you do a particular operation, it might change the value in a register, and if you've used a certain register by mistake, then you might find something strange happening. Anyway, I'm going to talk about the general purpose ones. We'll learn more about them later on anyway. But we've basically got these registers AX, BX, CX, DX. There are other ones. I'm going to talk about these for now. So these are just like general purpose registers. We can store values in these by doing code like this. So if I put move AX 1, 2, then what this means, and these operands work in the reverse order to what you might expect. So what this means is store this value, this literal value, inside AX. So it's going to store that value in there. And if I do, it gets more confusing when you have something like this. So let me just check that compiles. I want to make sure we're writing the right code. Yeah. Now if I do this, move so what this is saying now, it's saying, remember which way around it goes, it's saying move AX, the value of AX into BX. you can think of it, when it says move, you can think of it as copy really. It's like copying the value. It doesn't, the value will stay in AX until something else changes it. Okay, so we can move one register to another register, and this can happen very quickly. That's why we use registers instead of accessing memory, main memory for this kind of stuff. Now, just one note on these registers. I'll talk about, well, I suppose I can talk about it now, it makes sense to. When we start our computer up, it runs in, our x86 computer, it runs in 16-bit real mode, which is a backward compatibility mode. So even though you might have a 64-bit processor or whatever, when your computer starts, it will start in 16-bit compatibility mode. So when I talk about these registers, AX and BX, the values they store are 16 bits, so they can hold 2 bytes. Later on, when we look at switching into 32-bit mode, and it's similar for 64-bit extended mode, it just means that aside from other things that the process makes available in those modes, one of the things it does is it means that we can then add together and treat numbers, move data around in 16-bit or 32 or 64-bit chunks at once, so like in one instruction or in one move statement. If I wanted to move 32 bits or manipulate 32 bits in 16-bit mode, I have to treat it as 2 16-bit values, and that's why when we basically add in the bit width to the processor, it means that we can process data much faster, because we can handle larger values in fewer instructions. Okay, so we're running in 16-bit mode, so these registers hold 16-bit values, so that means I could put move CX, something like this, OX 1, 2, 3, 4. Okay, so I can store that in CX. Let's just compile that. Oh yeah, so I made a mistake there, so my assembly told me. Okay, so there we go, it compiled. So, okay, I can store that value in there. If I put something like this, 5, 6, let's see what happens. Oh, it says word data exceeds bounds down here. So word is 16 bits in this case, and now I'm trying to write a value that's bigger than 16 bits. So there we go. Now, often when we're manipulating the registers, it's useful to also treat it as 2 8-bit values. We'll see in a minute when I look at interrupts why that is, but when you see AX, it just means the full 16-bit register. Now if I put move DL OX 1, 2, then what this is saying, it's saying in the DX register, with the lower byte, move this value into it. And if I do the same like this, so DH, it's just saying the same for the high byte. So if I put OX 3, 4, then it's saying move this byte, OX 3, 4, into the high 8 bits of the register. So we can treat it as separate values like that, as separate 8-bit values. Okay, that's probably enough on register for now. We just need to know that we can use those to store values in, and I'm going to show why that's important. But also some of those registers are expected by certain bits of code, like when you call a function, for example. We will look at functions later, but when you call a function in assembly, it basically amounts to jumping to an address. And if you want to pass arguments to that function, then you can use registers. You can store a value in a register, like AX, and then when the function that's called wants to use that parameter, it knows to look in AX. Well, it doesn't know to look in AX, it expects to. So that means you need to know which registers it's going to use to do that. We're going to look at interrupts now, so we'll see why this is important. So we're nearly there now, we're getting closer. Now, what we want to do, I mentioned earlier in the last lecture that BIOS is the thing that gives us some basic input-output, so that we can use the machine before we have an operating system. And the BIOS is implemented on a chip, usually stuck in the motherboard somewhere. And this means that, well, we know that when the computer starts, we see the screen come on and we see some text on the screen usually. So we know that somehow that computer is writing to the screen, and it's BIOS that enables that. And we also know that BIOS can read the boot sectors from the disks, so it has some low-level ability to read from these different devices, or the way they connect to the computer, the buses that they connect to. So we know it can do that stuff. So now what we're going to do is figure out how we can use BIOS to help us to print something to the screen. Now, the thing is, somewhere in BIOS, somewhere in that chip, which BIOS gets loaded into memory when the machine starts, so somewhere in memory there's this BIOS code that was loaded, and somewhere in that code there's a piece of assembly code, well, machine code it will be, a piece of machine code that knows how to tell the screen to print a character. And so what we want to do is run that code to print a character that we choose to print. The problem is that we don't know where in memory that is. If we could find where in memory that instruction was, we could have a jump statement that jumps to it, and then it runs that code. Now the other thing is that that code will expect, if it's going to print the character, it will expect the character to be somewhere that it can find it. And in this case we'll see that it's often a register that it expects the value to be in. And so we'd need to store the ASCII value of the character we want to print into some register, jump to that code and run it, and then we could print something to the screen. But the problem is we don't know where it is. But this is where interrupts come in handy, because a fundamental thing to how computers and operating system works is that we have this idea of an interrupt. And an interrupt just means that when we write in some code, we can signal an interrupt, which is just, we signal it by an index number, an interrupt number, and the computer will then switch into an interrupt state. And all that means is that it knows that somewhere in memory there was preloaded an interrupt table, and this is something that BIOS sets up. And it registers some of its functions for like printing to the screen or reading a disk into the interrupt table. And the interrupt table just maps an index, an interrupt number, onto a piece of code, a handler. And then whenever we call that interrupt with that particular number, it's going to send the processor will jump to that interrupt handler, execute that code, and then it will come back to us when it's finished. So this is useful because we don't need to know where in BIOS that code is, we just need to know that BIOS, thankfully for us, BIOS set up a handler for a particular interrupt that we do know that's well documented to print a character to the screen. Okay, so we're going to do that now. Right, so let's print a character. And again, remember we've got no operating system now, so if we can just print a single character without using an operating system, just using BIOS, then that's pretty good. It's a nice start. So let's get rid of these things. Now, let me just say, the machine code or the assembly instruction to call an interrupt is this int instruction. So if I put OX10, then this will call interrupt 10. So whatever index 10 relates to in the interrupt table that was set up somewhere in memory by BIOS, then when I call interrupt 10, it's going to send the CPU into an interrupt state. It's going to jump to the handler, it's going to run that handler code and then come back to me. So first of all I need to know which interrupt I want to call before I do anything. So I'm going to find that out. So, well, I've actually got the information here in front of me, but we're going to use well, we're going to call interrupt 10. Okay. Now, the way that the interrupts work with BIOS, the way it's set up, is that we have an interrupt number which relates to an index in the interrupt table, and inside the handler mapped from that particular index, BIOS has then got kind of like a switch statement you can imagine it as sub-handlers. So the first thing it does when it calls that handler for that interrupt, so interrupt 10 in this case I'm using, which is it's an interrupt for certain BIOS functions, and in this case it's one of them is going to let us print to the screen. So when BIOS, when that interrupt gets called, it enters a piece of BIOS code that has a switch statement that then looks at one of the registers. In this case it's using AX register for another value, which then determines which subhandler it calls. So you kind of use these interrupts and the registers to select particular functions from BIOS. And again, because it's an interrupt, I don't need to worry about where that code is in memory, because it's mapped to in the interrupt table BIOS already. And this is important because it means that the BIOS code can move around in memory on perhaps different hardware, means that it has to load at a certain address. So we don't need to know where it is. So I'm going to call interrupt 10. Right, if you want to find out these BIOS interrupts, you can Google on the web, you can find a list of, it will give you a table of all the interrupt numbers and all the register values that you need to set to call those particular functions, like to print to the screen or to do a beep or something like that. In this case we're going to print to the screen. Let's get on. Okay, so this particular function that we called, and it's a scrolling teletype BIOS routine, which just means that it will print characters. If we call it, it will print a character, and if we call it again, it will print a character next to that character that we printed before. And this is useful. So let me just write the code and get on with it. So if I put move AL H, now what this is doing, it's in the lower 8 bits of the AX register, it's going to move the ASCII code for the letter H. Okay. And the other thing we need to do is, remember I said that the handler that gets called when the interrupt 10 fires expects to know which subhandler to call, and it expects to find that subhandler in AH. And in this case I'm going to be using OXOE, and this is the scrolling teletype, so I'll put a comment in there. BIOS scrolling teletype function. Right then, what have we got here? Let's have a look. So we're selecting a particular function that we want to call in BIOS. We're passing in an argument to that function. In this case, BIOS expects it in AL, the lower bits of the AX register. And then we're calling the interrupt for a particular set of BIOS functions, and this is going to cause our CPU to jump to there, and then hopefully this should print something to the screen, if I've not made a mistake, which is very easy to do when you're writing assembly. So we compiled it, that's good. Let's just look in our hex editor to see what it looks like. Okay, we see some bytes in there for our instructions, and we see an H there, which is the H that I put in. It's the correct length, so that looks good. So now we should be able to execute it. So we use QEMU. So it's booted it, but it's not displayed a value in there. Okay, so let's just go back and check that I've got this right. So what could go wrong in this case? So like I said, it's easy to make mistakes. Okay, we've got okay, here's the first mistake then. I've got a jump, endless jump before my code runs, so it means that this code will never get executed. It's a good way of seeing how this works, but it shows it's easy to make mistakes when writing assembly, but it's good fun as well, just to see why you made mistakes and figure it out. So what I want to do is I want to move this jump, and another way I can write this jump using the dollar sign, just to show this, is to put jump dollar, which just means jump back to the current instruction. So this is going to give me an endless jump. So let me write a comment there so I know what that means. Now the reason I put a jump in my boot sector at the end of my code is that we don't want to allow the computer to carry on executing all the random bytes in memory, because we don't know what's going to happen. Now, okay, the computer might just fall over, but it is there is a slim chance that some of that random data could be code that, you know, it could call a BIOS function to say format the disk or something like this. It is possible that something like that could happen. If you imagine all of that memory that it's going to churn through. So I put this endless jump on the end of my code to make sure that I never escape this. It just keeps looping. So this should print something and then loop. There we go. So there's RH. It's a nice result, really. Now, if you talk to most people and you say I can print an H on the screen on my computer, they'll probably say, well, you know, a 5-year-old kid could do that with a bit of Python code, and they could do, which is good. But the thing is, here we're running at the lowest level in the computer. There's no operating system. We've not even, you know, we're just using BIOS to do the stuff. We've not got anything, no APIs to let us, you know, do something. No Python modules or Java modules. We're just working at the lowest level. And this is the early stage of when the computer boots. So we've printed an H, and that's pretty good. So let's just, like I said, we were going to have a function. We were going to have a boot sector that could say hello world. So let's just make that true. And then I think our work's done. I'll just summarise this stuff. But I can do that by just replicating these lines here. We can be more sophisticated later on, but I'm just going to print single characters for now, because I think we've probably learnt enough today. There we go. Let's compile it and let's run it. Hey, there we go. So it says hello. And because this is the BIOS teletype function, and there are different BIOS functions for printing strings in different ways. You know, like for printing at particular locations on the screen, or in different colours and stuff like that. But this one just prints each character one after the other. So there we go. So we've got a boot sector that says hello. I could write that to an ISO file, and I could run that. I could restart my computer with a disk in it, and it would just run my code that prints hello. So this is good. Let's just check we've covered everything now. Yeah. So we've had a look at how to assemble code. We saw how it's easier to do that than it is to write in the hex editor, especially because we can use labels for to represent offsets in the file, so we don't have to remember which byte, the particular location of a byte in the file to jump to that particular code. We just have a label. We also saw how we could pad it out to 512 bytes using just a few of the assembly like symbols, like the $sign. We looked at registers, so how the CPU can store stuff in registers, general purpose registers, and we looked at interrupts, and we saw how the use of registers and interrupts is a very primitive way of calling functions, and that's how we call functions in BIOS. We set some expected values in registers that BIOS expects, and then we call an interrupt. An interrupt we call with a certain number. In our case, we used hexadecimal 10, and all that does is it causes the CPU to jump to that particular index in the the CPU looks up the index in the interrupt table, and the interrupt table just maps that index to an address somewhere in the BIOS memory that is the start address of the BIOS code to do printing functions. And in that code somewhere, later on, if we write some code for printing out memory, we could search for the BIOS code in memory and print it out to see what it is, and we could probably even extract it from memory and sort of disassemble it back into assembly to look at how it works. But there'll be some bit of code in there that looks a bit like a switch statement, and if else, and it looks in let me just check which register it was. It looks in the AH register, so that the high 8 bits of the AX register, and it uses this number to select a particular function, so this is teletype, and then it looks in the AL, the low 8 bits of the AX register for the character to print for the ASCII value. So that's how it works. So we call the function in BIOS, and that, I think, is the end for today. So, so now we can write some assembly code for a boot sector. Next time we're going to learn more about assembly, and we're going to learn about things like stacks, and later on calling functions. And we're going to also look more about the CPU, how we can manipulate it to do certain things. And much later on, we'll look at how we can switch from 16-bit mode into a 32-bit mode, or it will be similar for 64-bit mode as well, which is what the operating system has to do when it's booting. It wouldn't be possible. Some older operating systems, like, I think, I might be wrong, but I think like Windows 95, they would run in 16-bit mode, and that was it. Whereas later operating systems, Windows 2000, it would boot up into 32-bit mode, and it would run in that mode. And it's not just the width of the bits. There are, like in 32-bit mode, it's got like protected memory space, so it can protect one process from another, which is specifically to help operating systems be more stable. We can look at this stuff later on, but you start to understand like why like an operating system like Windows 95 is much less stable than something like Windows XP, and it's possible for one process to trample over the memory of another one by mistake. So anyway, more on that later, but thank you very much. I hope that was useful, and we'll have another lecture soon. Okay, thank you, bye.